the first panel. And our first speaker is Jeffrey Sheehy. Dr. Sheehy is NASA's chief engineer in the Space Technology Mission Directorate. His PhD is in chemical physics from Indiana University. He has over 25 years of experience in space technology, R&D, and demonstration, including at NASA's Ames Research Center, Ames Research Center, and its Marshall Space Flight Center, and at the Air Force Research Laboratory. He is author or co-author of more than 40 peer-reviewed journal articles and 30 technical reports. Jeffrey Sheehy.
Okay, should I use that thing? All right, great. Can you hear me? All right, excellent. I figure if we all parade to the podium and back, we'll just use up useful time. So I'll speak from here. Maybe I'll stand here. That might be easier. I can see everybody. Well, you know, this is an auspicious time, I think, because just the fact that we're having an event like this means that there's serious consideration of actually building and fielding space reactors. Alan talked about the different types of reactors that we're looking at for different implementations, but it's kind of exciting to be in a position to actually be developing technologies, looking forward to actually building and flying space vision systems. So it's been a very long time. SNAP 10A was a very, very small child at that time. So it's an interesting time. I think there's a few misconceptions. I'll try to correct them or address them as we go along. You know, we don't do what we do in secret at NASA. We're the civilian space agency, and we are compelled to tell OMB and tell Congress frequently, multiple times a year, what we're doing. So nobody should be surprised about the kilopower test that was done in Nevada about 18 months or so ago. We were informing Congress and the administration all along the way, and we have to do that for everything we do in NASA. So we'll go to the next slide. I guess if I was standing over here, I can do that. Yeah, there we go. I got it. Thank you. Beautiful. One thing I wanted to highlight is, you know, I made a comment to Lee last week. Lee Mason's here. I'm not the only guy from NASA. There are several of us here today, but I made a comment to Lee. We work together a lot, and that boy, the last couple of months seems like we spend all of our time on nuclear, on either the surface power or the nuclear thermal propulsion. And they're very high priority projects right now. And of course, as part of the reason we're here, they're getting a lot of visibility. But we do a lot of other things in space technology. Lee and I probably have 100 or more projects that we oversee at varying levels. And it's just in space propulsion, there are 4 that I've highlighted here. But the reason we're here today, or part of the reason, is the NTP project. So I'll describe just very briefly at the top level what we're doing there. And in space power, similarly, there are multiple activities that we have ongoing, but the one that brings us here today, as Alan mentioned, is the fission surface power. I call it design, development, and demonstration. The 3Ds there, kind of progressing through the technology development till you can actually have an operational system. So I'll talk in detail briefly. I appreciate Fabia giving me 10 minutes of her time, though.
I don't know.
Not happening, I guess. So I'll talk briefly about our fission surface power activities. The main thing is we're mission-driven at NASA, and it probably goes without saying generally, but it's worth saying here because the missions have. Oh, I didn't mean to do that. There we go. The missions have programmatic constraints, and I put the arrowhead both ways on this because sometimes the programmatic constraints tell us what missions we can do, and inside that programmatic constraints box are policy items as well. I don't need to you know, gloss over that. I try to make the slide kind of simple. There are other factors that contribute here, but the missions give rise to mission performance requirements, and then those give rise to system performance requirements, and the programmatic constraints and the system performance requirements lead us to a system design. Our designs have to meet requirements that perform actual missions, and some of our requirements in NASA are unique. We've got to launch these reactors, as was mentioned. We've got to land a surface power system on another planetary body, on the moon or on Mars. And so that brings with it mission performance requirements and system performance requirements that influence the design. If our design doesn't meet the requirements, we can't do the mission. If our design doesn't address the programmatic constraints, which include not only things like policy, but things like costs and schedules, we can't do the mission. And so there are other factors that contribute. I've listed a couple of them here. I put technologies on there because we're the Space Technology Mission Director. So of course, we're very interested in developing and utilizing new technologies to enable new types of missions or greater capabilities. And so the availability of the key technologies feeds into the system. And then there are implementation limitations. Can you manufacture it? Can you test it? With nuclear thermal propulsion, one of the things we're wrestling with is how would we test a nuclear engine? We wouldn't do it the same way they did it in the 1960s and 70s. I guarantee you that. Times have changed, and sensitivities to that sort of thing have changed. And so testability is a key driver in a system design many times. You know, so we have missions, right? And everything feeds back to the missions. And probably our biggest mission at NASA, our highest profile mission in NASA right now is what we call kind of colloquially as boots on the moon by 2024. The Vice President went to Marshall Space Flight Center in March and gave a speech, and this is an excerpt from the speech, but he said we want to return American astronauts to the moon. More recently, the administrator's been saying the first woman and the next man will step on the moon within 5 years, and the President has directed the NASA administrator accomplish this goal by any means necessary and focus on the mission over the means. And so boots on the moon by 2024, that's a big deal, high profile mission that comes to us from people sitting just down the street here at Pennsylvania Avenue, in a big white building and then a weird French looking building next door to it. Sustainable presence by 2028, that's another aspect of the task that's been given to us by the President. Going to the moon to stay. The fact sheet that was issued in conjunction with the event at Marshall in March said that we want to land on the moon's south pole. This is important because it's a shadowed region. Some of the regions there are permanently shadowed. Some of them receive a little bit of sunlight. And so you need a power infrastructure that works where there's no sunlight to establish a sustainable presence, to have a sustainable presence, to utilize the resources that are on the moon. That's power hungry activities. And the things that we're doing on the moon are laying the groundwork for developing the capabilities that allow us to move on to Mars. And that's the last part of the statement there. So these are our major missions right now. And in space technology, the organization, the chunk of NASA that develops new technologies, we aren't going to have a lot new ready by 2024, but we expect to have several new capabilities ready by 2028. Anything that's going to be done by 2024, the technology would have to be available now. So we have been working on some things that'll become available that will make its way into those missions. But we're not going to have a fission system on the moon by 2024, but looking forward to a sustained presence later in the 2020s and beyond that, that's when we would need that sort of capability. So the key technology challenges that feed those missions, those major mission elements, are listed here. I didn't put a summary of each one on the slide because it would have just cluttered the thing and taken a lot of time to talk through that. But you can see sustainable power and advanced propulsion as the first two items I've got there. And then if you look at the others, turning lunar ice into water, turning regolith into oxygen, converting water to cryogenic propellant, many of those would require power. So the first one, sustainable power, is something that would be necessary to do several of the others that would be associated with exploring and utilizing resources on Moon and ultimately on Mars. So these are the technology areas that are, we consider the key areas to be developing new capabilities in Space Technology Mission Directorate at NASA. So just briefly on the nuclear thermal propulsion project, and then briefly on the surface power, efficient surface power project. So for NTP, the key benefits are perceived to be and analyzed to be faster transit times, depends on the performance of the system and a number of other factors, including orbital mechanics, but you can get faster transit times. You can reduce the architectural mass, the number of heavy lift launches that you have to do to get all the infrastructure you need to perform a Mars mission, certainly. Can be less with an NTP capability because it's a higher performance, lot more miles per gallon, about double the miles per gallon you get with a chemical propulsion system. So it's a fuel economy. And then increased mission flexibility. That takes the form of wider launch window opportunities, as well as abort capability. Instead of being able to abort maybe a day into the mission, like you could with a chemical system, you could abort a few months into the mission if there was some reason that you needed to do that with the NTP fuel efficiency and power density capability. And so the main project objective, as you see there, is to determine the feasibility and affordability of an LEU-based NTP engine with solid cost and schedule confidence. Even walking around NASA headquarters, you can hear people say, oh, that'll cost $50 billion to develop an NTP. We could never do that. Well, we would actually analyze it quite extensively and be able to put in front of decision makers that this is what it would cost, this is how long it would take, and then allow a determination of whether it's worth it to the Mars human mission architecture to develop NTP. LEU-based, HEU-based engines were tested in Nevada in the 60s and 70s. There's a development there that's a heritage that we can build upon in many respects. But looking at an LEU-based system as an alternative to that has been an aspect of our current project. So I listed the major project elements there. I won't go through them, but you can see that it's quite a comprehensive set of activities focusing on fuel, design, fabrication, and testing, and developing conceptual designs for the reactor and engine, and then doing the feasibility analysis of what it would cost to develop NTP through the first flight set. So that's kind of just a quick overview of our nuclear thermal propulsion project. For efficient surface power, well, as I mentioned, about 18 months ago in Nevada, we did the test. This system was a 1 kilowatt electric reactor, about 4 kilowatts thermal. It was designed with flight-like components. It was integrated into a flight-like power system. It was tested at flight-like conditions, including full thermal power, various operating conditions. Even looked at, kind of introducing faults into the system and seeing how the reactor would respond. It was done in a vacuum environment. We used the facilities at the Nevada National Security Site, the device assembly facility, and the personnel and the capability they have there. I've got a few pictures, but in the bottom right, I don't expect you to analyze the details, and in fact, to explain the details, it would take Lee Mason, who's much more conversant in it than I am. But the point is, we produced data. The reactor, it was a very successful test. It showed fast startup to full temperature and power, predictable and well-behaved performance, and even multiple fault tolerance without power loss. So now, why did we do the test the way we did? That's a important question, and it's part of the reason I think for for this gathering, and there is rationale for doing the test the way we did. It was mentioned earlier about mass, and yeah, we got to launch and we got to land these things. So mass is important. In space flight, we are always seeking. I talked about design earlier, the factors that go into design. We're always looking for everything in space flight is complicated, but we're still looking for the least complex, the least costly, and the least massive system almost every time, because the cost associated with launching a kilogram of mass into Earth orbit is still several $1,000s. And so every kilogram helps. And if you have to put it on a lander, you got to put it on a lander that exists. So in any case, we thought the mission capture for a small fission reactor would be the greatest. The component availability, there isn't a low enriched uranium fuel that was readily available that we could use in the reactor, but there was UMOLY from DOE, and so we could run a test and really do a validation of the ability to develop and test a space reactor in today's environment. Hadn't been done in 50 years. The facilities were available, that we could demonstrate the capability to develop a space reactor, as I mentioned. The affordability and timeliness of the project were important. We did this project for $12.7 million NASA cost in 3.5 years. It's really amazing. It's a testament to not only the NASA people, but the DOE people that were involved in this, NNSA, Los Alamos folks, and others. Managing technical and programmatic risk is always important. It goes into those programmatic constraint spots I had on the previous slide. And then there are cross-agency benefits. The NNSA saw enough benefit to the test to actually co-fund it. They put in $5 million and a lot of in-kind support also. So I'm almost done. Well, this is really the last slide. We have ongoing right now a fission surface power design study in conjunction with DOE. Our main interface there is INL through Tracy Bishop at DOE, and then INL is pulling in Los Alamos to work on several of the tasks underneath the study. It's looking at a 10 kilowatt class, what we're calling a capability demonstration. We don't intend to just land this reactor on the moon, run it for a while and say, hey, it worked, now somebody could use it for something. We actually tend to use this reactor for some useful power, to provide power for some useful purpose while it's on the moon. So it's not just a tech demo, it's a capability demo. The final report of this study is due sometime in the early part of 2020. We're still refining that date as we just got going on this study within the last 8 weeks or so. You can see the primary responsibilities divvied up there. And I won't go through all this, but this shows what the final report will include. It's quite comprehensive. And you can see on the second dotted bullet there under the final report, it includes LEU and HEU in the trade space. So the fact of the matter is NASA hasn't decided yet how we will fuel, what will be the fuel for the surface power system. There are a lot of constraints, there are a lot of design requirements that will feed into that, but LEU and HEU are both in the trade space at this point. And what the goal of all this is to produce the kind of data that NASA would characterize as a mission concept review. So it's a mission concept review level of data for one or more different options for a 10 kilowatt flight demonstration of the moon. The date there is 2027. I told Alan I would say plus or minus a year, but it's almost certainly not going to be minus. But that's the kind of tentative planning date at this point. We don't have the schedule. One of the things this study is going to do is lay out the schedule. Seems like this is going in and out.
Yeah,
so
sorry.
Talk a little louder. But that's really what I wanted to leave with you today. That just to summarize the activities that we've got going on in nuclear thermal propulsion and the fission surface power, and to show you what the trade space includes for both of those activities, give you a sense that we've got to design the mission requirements, and that's what we're trying to do. So that's the end for space.
Thank you very much. Thank you very much, Jeff.